In this lecture video, we'll be looking at custom hypothesis tests in the context of the randomized complete block design. Now here's the agenda of what we'll be covering. We'll first look at the general form of hypothesis tests that we'll be looking at. We'll look at hypothesis tests involving differences between two treatment means. We'll look at hypothesis tests involving contrasts of two or more treatment means. We'll then look at hypothesis tests involving non-contrast linear combinations of one or more treatment means. And then finally, we'll look at hypothesis tests involving individual treatment means. So let's first look at the general form of hypothesis tests that we'll be looking at. In general, hypothesis tests in this collection of tests will involve a linear combination of the treatment means that is of the form as follows. It's a sum, j going from 1 to t. So we're summing up over all of the treatments in the treatment structure, j going from 1 to t, a sub j times mu sub j. The hypothesized value of such a linear combination will be denoted by lambda sub 0, which will stand in some relation to the linear combination of the treatment means in the hypotheses. Now, as usual, there will be a two-tailed test, a left-tailed test, and a right-tailed test available to us. The general form of the test statistic for this collection of tests can be expressed in terms of a t-statistic, so we'll call it t-calc, which has the standard form of a t-statistic, a ratio, the numerator being the difference between the estimated value of the linear combination minus the hypothesized value of the linear combination. The denominator is the estimated standard error of the estimate of the linear combination. Now, this is the general form for the test statistic. The specific form will depend on the expression for the estimated standard deviation of the estimate of the linear combination, which will depend on the nature of the linear combination about which we're testing a hypothesis. Now, before we can talk about critical points, we need to talk about reference distributions and so forth. In some situations, in the context of what we'll be looking at, the actual reference distribution will be known, and the appropriate critical point will also be known and will be calculable. In other situations, the actual reference distribution itself will not be known, and therefore the actual critical point will be unknown as well. This will require finding an approximate critical point using any one of several approximation methods that are available. Now, whether or not the actual reference distribution is known will depend on the nature of the linear combination being tested, which in turn will determine the sampling distribution of the test statistic, which, under the conditions of the null hypothesis, determines the reference distribution for the test. So let's look at a particular situation here, a hypothesis test involving differences between two treatment means. So, in other words, pairwise differences. And so you'll see here that we have the three types of tests that we typically have. We have a two-tailed test, a left-tailed test, and a right-tailed test. The two-tailed test has a null hypothesis that says that the difference between treatment means mu sub j and mu sub j prime is equal to some hypothesized value, lambda sub 0, against the alternative hypothesis, which says that that difference is not equal to lambda sub 0. The left-tailed test has a null hypothesis that says that the difference between two treatment means, mu sub j and mu sub j prime, is at least lambda sub 0, against the alternative hypothesis that says that the difference between the two treatment means is less than lambda sub 0. And then finally, the right-tailed test has a null hypothesis that says that the difference between the two treatment means mu sub j and mu sub j prime is no more than lambda sub 0, against the alternative hypothesis that says that the difference between the two treatment means exceeds lambda sub 0. So each of these hypotheses are expressed in terms of a difference between the two treatment means. And note that in many situations, lambda sub 0 may be 0, but there will be many situations where lambda sub 0 is not equal to 0. It'll be some other number that's meaningful in the context of a given situation. Now, the specific form of the test statistic for tests like this involving differences between two treatment means is given by the following expression. And you'll note that t-calc, the test statistic, has a numerator that's equal to the difference between the estimates of the corresponding treatment means, so mu hat sub j minus mu hat sub j prime. All right, and then from that we subtract the hypothesized difference, lambda sub 0, and then we divide that difference by the estimated standard deviation of the sampling distribution of the estimator of the difference of the treatment means, which in this case turns out to be the square root of 2 times the mean squared error from the ANOVA table divided by r, the number of blocks, or in this case the number of replications. Now, in this situation, the reference distribution is known. In particular, the reference distribution is the t-distribution with degrees of freedom equal to r minus 1 times t minus 1. Now, you'll recall that this is the number of degrees of freedom associated with the mean squared error in the ANOVA table. And so we have here the rejection criteria for the two-tailed test, for the left-tailed test, and for the right-tailed test. And so these are, as you would expect, these are the same as you would have for any other t-test, with these specifics being the degrees of freedom for the test. Now, an equivalent procedure for performing the two-tailed test is to use an F statistic. All right, and so we would call this F-calc. And F-calc is equal to the square of the difference between the estimate of the difference between the treatment means and the hypothesized value of the difference between the treatment means, divided by the estimated variance of that linear combination, which again is equal to 2 times the MSE divided by R. So that is the F statistic, F-calc, for this version of the two-tailed test. The rejection criteria would be to reject the null hypothesis if F-calc, the test statistic, is greater than the upper alpha percentage point of the F distribution with 1 numerator degree of freedom and denominator degrees of freedom equal to r minus 1 times t minus 1. All right, next we'll look at a hypothesis test involving contrasts of 2 or more treatment means. And so here we have the hypotheses, and these look very similar to the hypotheses in the previous subsection, the only difference being that now we're talking about not just a difference, but really any contrast between 2 or more treatment means. And so we'll express that contrast as a linear combination here. Now the sum A sub j times mu sub j equal to lambda sub 0, being the null hypothesis for the two-tailed test, against the alternative hypothesis that the sum A sub j times mu sub j is not equal to lambda sub 0. And then the appropriate types of null and alternative hypotheses for a left-tailed test and a right-tailed test. All right, so again, the linear combination, and in particular, in this case, the contrast between 2 or more treatment means is being expressed using this linear combination notation. Now, the specific form of the test statistic in this case has this form. So again, it's a t-statistic. The numerator of that t-statistic is the point estimator for the linear combination, so the sum A sub j times mu hat sub j. From that, we subtract off the hypothesized value of the linear combination, and then we divide that by the estimated standard deviation of that estimated linear combination, which is equal to the square root of 1 over r being the number of blocks, times the sum of the squared A sub j's, times the mean squared error from the ANOVA table. And then we have the usual rejection criteria involving critical points from the t-distribution with degrees of freedom equal to r minus 1 times t minus 1. Now we can also use an f-statistic in this situation as well if we happen to be performing a two-tailed test. And so in this case, f-calc would be equal to the square of the difference between the estimate of the contrast about which we're testing hypotheses minus the hypothesized value of that contrast divided by 1 over r times the sum of the a sub j squared values times the mean squared error. Again, we reject the null hypothesis if the test statistic f-calc exceeds the upper alpha percentage point of the f distribution with one numerator degree of freedom and r minus 1 times t minus 1 denominator degrees of freedom. All right, now let's look at something even more general, hypothesis test involving non-contrast linear combinations of one or more treatment means. The hypotheses that we have here look identical to the hypotheses that we had in the previous subsection where we were looking at contrasts of two or more treatment means. But now in this situation, we're not necessarily looking at a contrast, all right? And so the sum of the a sub j's can be something other than 0. The specific form of the test statistic for tests involving linear combinations of treatment means, as we have here, is given by this expression. So it's a t-statistic. So we'll call it t-calc. The numerator is equal to, well, looks like it did in the previous section. It's the difference between the estimate of the linear combination, all right, minus the hypothesized value of the linear combination. And then we divide that by the estimated standard deviation of the estimate of the linear combination. Now, this is where things get a little more complicated because we're looking at a linear combination that is not necessarily a contrast. All right, and because of that, the sum of the a sub j's is not equal to 0. And so the form of or the expression for the estimated standard deviation of the estimate of the linear combination is more complicated. This involves both the mean squared error and the mean squared for blocks. And so this is the expression for the estimated standard deviation of the sampling distribution of the estimator of the linear combination about which we're testing hypotheses. All right, so now let's look at the rejection criteria. And you'll notice here that the critical points all have a star in the superscript. And that is because in this particular situation where we're testing hypotheses involving non-contrast linear combinations of the treatment means, the sampling distribution of the test statistic t-calc is unknown. And the reason, again, for that is because the estimated variance and estimated standard deviation of the point estimate of the linear combination of the treatment means involves more than one estimated variance component. In this case, it involves the mean square for blocks as well as the mean square error. And so because of that, the exact number of degrees of freedom associated with the sampling distribution of t-calc is unknown, and so we're not able to get an exact critical point in that case. Now, what do we do in this situation? The same thing we did when we were looking at estimation of non-contrast linear combinations of treatment means, and in particular when we were looking at constructing confidence intervals for those non-contrast linear combinations of treatment means. And so the same methods of approximation used for constructing those confidence intervals are used in the context of hypothesis testing as well, and in particular hypothesis testing involving non-contrast linear combinations of the treatment means. And so for convenience, I have included those two approximation methods that we looked at on the following slides. And so let's take a look at those. And I'm not going to read over these or explain these in detail. We've already done that previously. But just note that these formulas apply as well. So here is the first approximation formula. We've called this approximation 1. a method for approximating t star sub p. And I'll just say that in the previous context, when we were talking about confidence interval estimation, we called t star sub p an approximate interval coefficient, okay, because it's the interval coefficient that we multiply against the estimated standard error of the point estimator of the linear combination. But in the context of hypothesis testing, instead of calling it an interval coefficient, we're going to call it a critical point, all right, to be consistent with the context in which we're discussing it. So this is approximation method or approximation formula 1 for coming up with an approximate critical point. And the other method, the approximation method 2, all right, is given by this slide. And we can see here that in this particular approximation, what we're doing is approximating the degrees of freedom, and then we obtain the upper alpha over 2, in this case the upper alpha over 2 percentage point, from that approximate t-distribution, the t-distribution possessing the approximate degrees of freedom given by this formula. So in approximation method 2, what we're doing is we are approximating the degrees of freedom associated with the estimate of the variability of the estimated linear combination. All right, so on this slide we're estimating the degrees of freedom, whereas in approximation 1 what we're doing is we are taking a weighted average, all right, of the critical points from two different t-distributions, a t-distribution with r minus 1 degree of freedom and the t-distribution with degrees of freedom equal to r minus 1 times t minus 1. So two different approaches to getting an approximate t-value, an approximate critical point in this context. And often these two approaches will provide approximate t-values that are very close, but again, they're not exactly equal. All right, now let's look at a special case of the present context, hypothesis tests involving individual treatment means. And so again, let me go back one slide, what we've been looking at in the present situation are hypothesis tests involving linear combinations of one or more treatment means, and in particular non-contrast linear combinations of one or more treatment means. Now if we look at the very special case of that, of just one treatment mean or an individual treatment mean, which we can certainly do, then some of the calculations get simplified, and in particular the formulas for the approximate t-values simplify a bit, and so we'll look at that. But so in this situation, when we're looking at hypothesis tests involving individual treatment means, all right, so in the null and alternative hypotheses, obviously we would have just one of the treatment means. All right, this is a linear combination of the full set of treatment means. In particular, the treatment mean that we're interested in has a coefficient of 1, and the others have coefficients of 0. All right, so this does fall within the context of what we are currently looking at, and it's a special case of that more general context. So we have, with that in mind, we have three sets of hypotheses: a two-tailed test, a left-tailed test, and a right-tailed test. In each case, both the null and alternative have or contain statements involving only one of the treatment means. All right, so the specific form of the test statistic for tests involving individual treatment means is given by this expression here. And we can see here that in the numerator, we have the difference between the estimated value of the treatment mean minus the hypothesized value of the treatment mean. And then we divide that difference, as we always do, by the estimated standard deviation of what's in the numerator. All right, and so in that case, that would be the square root of the mean square for blocks plus t minus 1 times the mean squared error divided by r times t. So that is the formula for the test statistic when we're testing hypotheses about a single or individual treatment mean. All right, and then as is usual, we have corresponding to each of those three types of hypotheses, we have rejection criteria. So for the two-tailed test, we have a two-tailed rejection region. For the left-tailed test, we have a left-tailed rejection region. And finally, for the right-tailed test, we have a right-tailed rejection region. Now, because this is a special case of the more general situation that we're looking at, again, in this situation, the sampling distribution of the test statistic is unknown. And again, that's because the estimated variance and the estimated standard deviation in this formula here, we can see that that involves more than one variance component, more than one estimated variance. And so because of that, we don't know the exact degrees of freedom associated with that estimate, and therefore we don't know the exact sampling distribution. We don't know the exact t-distribution. And so in the present context of testing an hypothesis about an individual treatment mean, the formulas for approximating the t-value simplify a bit. All right, and so let me just scroll back a few slides here. All right, so these were the two approximation formulas that we looked at when we were looking at testing hypotheses about non-contrast linear combinations involving one or more treatment means. So this was approximation method 1 for the t-value, and this was approximation method 2 for the approximate critical point, or t-value. Now, in this situation where we're looking at just one treatment mean, obviously one of the coefficients is going to be 1 and the rest are going to be 0. And so what that results in is that these expressions for Q1 and Q2 are simplified, all right, and things kind of cancel out. And so when we look at that, this is what we get. So for approximation method 1, the critical point is given by this expression. And I'm not going to read through it. You can see here that things have canceled out somewhat, and we have a t-1 involved now that we can see. And so it is a bit simpler. We don't have to calculate Q1 and Q2. And then for approximation method 2, where we are obtaining an approximate t-value, an approximate critical point, by approximating the degrees of freedom associated with that estimated variance. This is the formula that we get. So again, the Qs, the Q1 and Q2 are somewhat simplified, and we see we have a t-1 roaming around in this formula, and we don't see Q1 nor Q2. All right, and so certain things did cancel out, but we do have this t-1 here, both in the numerator and in this right-hand component in the denominator as well. So those are the formulas, and again, these simplified formulas are only for the situation where we're testing hypotheses about individual treatment means. If we're testing hypotheses involving non-contrast linear combinations of more than one treatment mean, then we would need to go ahead and use these general formulas. And you could use these formulas if you're testing hypotheses about one treatment mean. If you do, you would get the same value that you would get if you use the simplified formulas. But I'm just providing the simplified formulas in these slides down here just to show you that they do simplify a little bit, and it may make it easier for you to calculate. All right, so let's look at an example. Now recall from example 3.1, in which an experiment was conducted using a randomized complete block design to generate data for comparing the means of 5 treatments. In that example, it was concluded that differences do exist among the 5 treatment means, but that analysis in and of itself does not tell us where the differences are. So a natural follow-up question would be, where do differences exist, and what are the magnitudes of those differences? Now, answers to these questions, the first question indirectly and the second question directly, are obtained via confidence interval estimation of linear combinations of treatment means. The linear combinations to be estimated are those that correspond to the particular questions of interest to the researcher. Example 3.3 investigated several linear combinations of treatment means via confidence interval estimation. Based on those confidence intervals, many conclusions can be drawn about how the treatment means are related. In this example, we will investigate relationships between treatment means by performing custom hypothesis tests about linear combinations of the treatment means. Now, this approach will or can be used to directly answer questions of the first type, that is, where do differences exist? However, it really does not provide as much information as confidence intervals regarding the magnitude of the differences themselves. On the other hand, hypothesis tests do provide information on the magnitude of the statistical significance of the observed differences, while confidence intervals do not provide that kind of information. So the implication of this is that one must not depend solely on hypothesis tests, nor solely on confidence intervals, when making inferences about treatment means and their relationships among each other. There is an overlap in the information that the two approaches provide, but there is not complete overlap. The two approaches supply consistent but complementary information that must be considered in order to draw conclusions and make decisions that are as informed as possible. So I've included the summary data and the analysis of variance table just for easy reference, and so you may want to pause the video or back the video up at some point as we get into these calculations, right, in order to see these values. But we have the, in addition to the raw data here, we have some summary statistics. We have the treatment sums, the treatment means, the uncorrected sum of squares for each of the treatments. And then we also have the ANOVA table here that we constructed back in example 3.1. And so let's first look at hypothesis tests involving differences between two treatment means. All right, so this was the first situation that we looked at in developing or looking at the procedure. And let's look specifically at comparing the means of treatment 1 and 2. And we'll do this via the difference mu1 minus mu2. And so our null hypothesis in this particular situation will be that the difference, mu1 minus mu2, is equal to a hypothesized value of 0 against the alternative hypothesis that mu1 minus mu2 is not equal to 0. The significance level, we'll use a 5% significance level. And the critical point, I'm going to use an F-test. I'll calculate an F statistic. We can do this again because this is a two-tailed test. And when doing a two-tailed test, it's really a little bit easier in terms of expressing the rejection criteria and so forth if we use an F-test. And so the critical point for the test will come from the F distribution with 1 numerator and 12 denominator degrees of freedom. And since we're testing at the 0.05 level, the critical point will be the upper 5th percentage point of this reference distribution. That critical point is 4.75. Now the test statistic, F-calc, is equal to the difference between the estimates of the treatment means minus the hypothesized value of 0, and then we square all that. And so you see here the numerator is equal to the square of the difference between 36.675 and 53.125. The denominator of F-calc is 2 times the mean squared error, which from the ANOVA table is 16.4774, divided by R, which in this case is 4. And so when we calculate this, we get a value for the test statistic equal to 32.845 rounded to 3 decimal places. Now, since that test statistic value of 32.845 does exceed the critical point of 4.75, we would reject the null hypothesis and conclude that the difference between the means of treatments 1 and 2 is not equal to 0, which of course is equivalent to the statement that mu sub 1 is not equal to mu sub 2. Now note that the p-value of the test is very small, being equal to this quantity here, 9.440 times 10 to the negative 5th power. So that's a very small p-value. And with this p-value, we get a very good sense of just how strong the evidence is against the null hypothesis. You'll recall that the smaller the p-value, the more evidence there is against the null hypothesis. And so while the hypothesis test really does not give us information about the magnitude of the difference between the two treatment means, it does give us an idea of the magnitude of the significance of the test. Now, as an exercise, what I'd like for you to do is to perform the rest of the pairwise comparisons between the treatment means. So there will be 9 left. All right, and so if you go ahead and run through these as for practice, you'll find that you get these results here. So these are the p-values that I've obtained for each of the tests. And you don't have to calculate the p-values. You can just, if you would like, you can use the test statistic and critical point method. In coming up with these p-values, I've used the TI-84 calculator. If you've got a calculator that will allow you to look up or calculate p-values using an F-distribution, then you can use that. You could also use SAS or SPSS or R or a package like that to compute these. All right, but you can at least look at these and tell whether or not you would reject at the 0.05 level of significance that you would be using in performing the test yourself. And so if you reject, if in testing a particular null hypothesis at a 0.05 level of significance, you reject that null hypothesis, you can come back here and you can see whether you would reject based on this result as well. All right, now let's look at the hypothesis testing results and the point and confidence interval estimation results for these pairwise comparisons. All right, and so again, these are, well, what I've got here, I've combined the two types of results. Combine the results for hypothesis tests, where the null hypothesis would be that each one of these differences is equal to 0, against the alternative hypothesis that the difference is not equal to 0. And the p-value column gives us the p-values for these results. In addition to those hypothesis test results, I've got the information that we came up with when we estimated each of these differences. We've got the point estimates for each of these differences, along with the approximate 95% margin of error associated with these point estimates. And then finally, we've got the 95% confidence interval for each of these differences. And so you can see here we're combining both the results from the hypothesis test and the confidence intervals to get as much information as possible about where the differences are and how big those differences are. All right, next let's look at hypothesis tests involving contrasts of 2 or more treatment means. And in particular, what we'll look at is comparing the average of the means of treatments 3 and 4 with the mean of treatment 1. And so the null hypothesis will be that mu sub 3 plus mu sub 4 all over 2 minus mu sub 1 is equal to 0. Now, obviously, that's equivalent to the null hypothesis that says that the arithmetic average of the means of treatments 3 and 4 is equal to the mean of treatment 1, and the alternative would therefore be that those are not equal. And so expressed in terms of a difference, it would be that mu sub 3 plus mu sub 4 all over 2 minus mu sub 1 is not equal to 0. We'll use a 0.05 level of significance again. The critical point for this test will therefore be the upper fifth percentage point of the F distribution with 1 numerator and 12 denominator degrees of freedom, which again is 4.75. The test statistic is, again, I'm going to be using an F statistic. So F calc turns out to be equal to 0.6075, calculated in this way. And so you can see here that the numerator of F calc is equal to the numerator being equal to the square of the difference of the estimate of the arithmetic average of treatment means 3 and 4, so 30.275 plus 39.2 all over 2, minus the estimate of treatment mean 1, 36.675, divided by the estimated variance of this linear combination. So 1/4 times 3/2 times 16.4774, using this formula here. And so when we calculate that out, we get 0.6075 rounded to 4 decimal places. Now, since that test statistic does not exceed the critical point of 4.75, we would fail to reject the null hypothesis. Now, the p-value for this test is fairly large, 0.6649. And so again, we see that although the hypothesis test in and of itself does not provide really any information about the magnitude of the difference, and we know that we would not reject here, we do see through this hypothesis test via the p-value, we see that we get an idea of how significant the observed difference is, which is not very, right? We see that this is not even close to being statistically significant. Now, along with this hypothesis test, if we did want information on the magnitude of the difference between the average of mu3 and mu4 and mu sub 1, we could compute this estimate, a point estimator and also a confidence interval estimator. So the point estimate for this linear combination of the treatment means, and in particular it's a contrast, so the point estimator of the contrast would be negative 1.9375, and the 95% confidence interval estimate for the contrast would range from negative 7.354 up to 3.479. And so based on these two types of results, the results from the hypothesis test, where we failed to reject the null hypothesis, along with these results based on the confidence interval, we see that we would have no evidence at the 0.05 level of significance to conclude that a difference exists between the mean of treatment 1 and the arithmetic average of the means of treatments 3 and 4. So these are some examples of how we test hypotheses in the context of the randomized complete block design. It's important to keep in mind that the form of the test statistic, and in particular the form of the denominator of the test statistic, which is the estimated standard deviation of the estimate of the linear combination. If we happen to be using a t-test, if we're using an f-test, then the denominator for the test statistic is the estimated variance for that estimate of the linear combination. But the form of that estimate of variation is going to depend on whether or not we are looking at a contrast or not, because that's going to determine whether or not the mean square for blocks is part of that estimated variation. And that is going to depend on the nature of the linear combination. Is it a contrast or not? If it's a contrast, then things are quite a bit easier because we have a simpler form for the estimated level of variability associated with the point estimator of the contrast itself. In addition, if it's a contrast, the reference distribution for the test statistic, the sampling distribution of the test statistic is known, and so the reference distribution for the test will be known as well. On the other hand, if we're looking at a non-contrast linear combination of one or more treatment means, then things get more complicated in terms of calculating the test statistic itself. And then in addition, we have the issue where the true sampling distribution of the test statistic is unknown. Therefore, the reference distribution for the test is unknown. And so we're not able to know exactly what the critical point or points would be, so we have to approximate those. All right, now the next thing we're going to look at would be SAS code that we could use to perform these hypothesis tests and also to construct the confidence intervals for these linear combinations. And so here is a snippet of SAS code using proc mixed. And you've seen some of this code before. In particular, you saw at least some of this proc mixed code when we did the analysis back in example 3.1. But notice that I've added an option here on the model statement, and this option is called the denominator degrees of freedom. option, the DDFM option, and I'm telling it to use the Satterthwaite approximation. All right. Now, in order to correctly perform tests and calculate estimates of linear combinations that are non-contrasts, we have to include something like this. Now, there are other options that one can use. I've included this because this corresponds to method 2, the approximation method 2 that we've been looking at in the notes. And so if you work some examples or do some of the calculations that we've done and you need to compare to some SAS output, if you want to get the same kind of result, you'll need this option on the model statement. If you don't include this option, then ProcMix will not compute the tests nor the confidence interval estimates correctly in the case where you're looking at non-contrast linear combinations. Now, in the context of linear combinations that are contrasts, it will do it correctly. So, having said that, we can use the contrast statement to perform custom hypothesis tests involving contrasts, and we can use the estimate statement to calculate point estimates and confidence interval estimates for linear combinations of the treatment means. And so you've seen contrast and estimate statements before, previously in this course and in other courses more than likely. All right, and so to perform the hypothesis test where we're comparing treatment means 1 and 2, or equivalently, comparing the difference between treatment mean 1 and treatment mean 2 to 0, we would use these contrast coefficients. 1 is the coefficient on mu1, -1 is the coefficient on mu2, and then the rest of the coefficients would be 0. To perform the hypothesis test where the null hypothesis says that the arithmetic average of treatment means 3 and 4 is equal to the mean of treatment 1, or equivalently, that the difference between those quantities is equal to 0, we would use these contrast coefficients. We can see here that the coefficient on mu1 is -1, and then the coefficients on mu3 and mu4 are each 0.5. We would use the same coefficients for estimating each of these linear combinations, and if we wanted to construct confidence intervals for those linear combinations, those contrasts in this case, then we would include the option after the / the option CL for confidence limits. And so when we run this, what we get are the following. Here are the results of the contrasts. All right, so performing the hypothesis tests. And we see here that the F statistic for the test where we are comparing the means of treatments 1 and 2 is equal to 32.85. All right, and so if let me just scroll back here real quick, okay, to look at that test statistic. You can see here that we took it out to 3 decimal places, but if we round it to 2 decimal places, we get 32.85, which is exactly what we get with SAS. Okay, continuing on. The hypothesis test, where we're comparing the arithmetic average of treatment means 3 and 4 with the mean of treatment 1, that F statistic, rounded to 2 decimal places, is 0.61. And we see here that we get the same critical point, or I'm sorry, the same p-value that we got when we did it by hand. Actually, no, we don't. I got to go back here. I just checked, and we had a different value for that p-value, but I've corrected it here. We had 0.66 something, but the correct value is 0.4508, right? And I've calculated this using the TI-84. We can also get that from SAS, as you've seen, as we see here. All right, and in addition, we get the confidence limits we get the point estimates over here for each of these contrasts, and we get the 95% confidence intervals for those contrasts as well. So what I would recommend that you do is go back and compare these confidence limits to the values that we got by hand. All right, so this is the end of the example in terms of calculations. You can see how we performed these various hypothesis tests by hand, but you can also see how we can do this using SAS with the appropriate SAS code. One thing I do want to show you though is how I calculated the p-value using the TI-84. And so again, here I've got the TI-84 calculator screen, and if you press the second VARS key to get to the distribution menu, and then if you scroll down past 9, you'll see that option number 10 is the CDF for the F distribution. And so for this particular example, I plugged in a lower, the value of the test statistic was 0.6075 to 4 decimal places. And we want to evaluate the CDF. We want to essentially integrate the PDF from 0.6075 up to infinity. All right, so this is essentially calculating 1 minus the CDF evaluated at 0.6075. We've got 1 numerator degree of freedom and 12 denominator degrees of freedom. And so when we paste that into the calculator screen and then press enter to run that command, we get the p-value for the test of 0.4508, all right, which is what we got. Okay, so that is the end of that example and the end of this section of the notes, and we will continue with the next section in the next lecture video.